We created a linear model for a factorial 2x2 ANOVA, which is here and there. But this is traditional ANOVA. We're not going to see traditional ANOVA that you learned in previous courses. So we need to do the Bayesian ANOVA. In order to do the Bayesian ANOVA, we need to combine this newly formed linear model for ANOVA with what we already learned about the model comparison approach in Bayesian statistics. So we are just going to combine these two ideas in order to present a model for the Bayesian ANOVA. So, for the model, we now have 5 models. We did a model comparison approach in which we used 2 models before, but now we have 5 models. What are those 5 models? As always, we need to have a model of the null hypothesis. So the null model would have the beta 0 will be a parameter that will be estimated with the data, but for all the other 4 parameters, beta 1, beta 2, beta 3, beta 4, beta 5, 5 parameters, is fixed into 0. So it's not going to be estimated. For model 2, which I call variable x, it means that the variable x will have an effect on the outcome variable y. So basically, beta 0, beta 1, beta 2 will be estimated with the data, but beta 3, beta 4, and beta 5 will be fixed to 0. In the model 3 is variable z. That means that variable z has an effect on variable y. Now for beta 1 and beta 0, beta 1 and beta 2, which don't have anything to do with variable z, now is fixed to 0. Beta 3 and beta 4 will be estimated with the data, and the beta 5, which is the interaction parameter, will be set to 0. Now, model 4 includes both variables, x and z. So we've got beta 0, beta 1, beta 2, beta 3, and beta 4, but not the interaction. And finally, the model 5 is the model with both variable x and z and the interaction between these two variables. So that's the full model. We are going to estimate all the parameters from the data. Now, what's important is that because we chose this way of parameterizing the model, beta 0 will be the same value in all models. It is the mean total of y. So this is an interesting thing because we don't have to worry about estimating beta 0 because it will be the same in all models. Now, and remember, beta 1 and beta 2 are related, and beta 3 and beta 4 are related. So if beta 1 is estimated, then beta 2 will be beta 1 times minus 1. And if beta 3 is estimated, then beta 4 will automatically be beta 3 times minus 1. So in a sense, we've got only beta 1 and beta 3 to estimate, and beta 5. Now, that's still in the traditional realm of things. So now we move to the Bayesian. So in the Bayesian, we use the Bayes theorem to start, and this is the generic model, so we need to have one per each model, but so we put P or probability of M, which is model, given theta, but theta is in bold here because this is a vector of parameters, it's not just one parameter. So when you use a vector of parameters, which is in more than one, then you use bold instead of just the Greek letter. So probability of model, let's say model 1, given the parameter values and the data observed, equals probability of the data given the model and the parameters. So this is the sampling distribution for the data. What's the data? Well, the data is the observations we are going to collect in our study, and the specific statistic that we are interested in is the regression coefficient, or the coefficient in the linear model, the betas. But in order to differentiate the beta, which is a parameter in the population, from the statistic we calculate in our sample, we call it B instead of beta. So this will be the data we are going to collect and the statistic that we're going to calculate. And given the model, so the probability of the data will be different for each model. And the parameters, well, they come from with the models as well. Well, times probability of the parameters given the model, this is the prior on the parameters. The prior of the parameters in each model. And we are going to use the software JASP, and the software JASP uses a Cauchy distribution for the prior for the parameter values. So all the betas will use a Cauchy, and Cauchy, remember, is similar to a T distribution, and in a sense it's like a normal distribution, or has the characteristic of the normal distribution that is centered around a value and then is symmetrical. So in this case it will be centered around 0, and so positive values and negative values are possible, but the ones close to zero are more likely than extreme values. And this JASP will set the same prior for all the betas. And then P, probability of M, is the probability of the model, and that is the prior of the model. And in this case, because we have 5 models and we don't have any preference, we don't have any information which model is best at the moment, so we give the same probability to each of the 5 models. 5 models, the total probability of one has to be distributed equally among the 5 models, so it's 0.20 for each of the models. Now, probability of the data is probability of the data regardless of the models. So this is like a combination of the probabilities of the data of all the models. So this value, it will be the same value in all the models. So we can safely ignore that value when we compare the models. Okay, I'll show you how JASP presents the results. So JASP will show you the models, model 1, 2, 3, 4, 5. They will give you the variables. So this will be null, this will be variable x, this one will be variable z, number 4 will be variable x and z. Yes, variable x and z, and 5 will be variable x and z, and the interaction between these two variables. So then we start with the prior on the models. As I said, all the models have a prior of 0.20. They are equally likely before starting the study. And then, and this comes from this the P m, probability of the model in the theorem. Then probability of a model given the data is a shortcut for the posterior, for the models. Okay, we don't need to specify that is the parameters as well, but it's a given, and because you need to estimate the parameters, otherwise you cannot calculate the probability of the model. But so it's a shortcut for this, the posterior. Now these values are I made them up, so they don't have any meaning. Okay, so basically they do have a meaning, but they don't reflect any real world data. So in this case, what we have is that the probability of model 1, which is the null model, after observing the data, is 0.02. Now, the values of these five values should add to 1, like these five values added to 1. So now, we started with a probability for that model of 0.2, and now it went to 0.02. So it's much less likely after observing the data than when before observing the data. Now model 2, which says that variable x is the only variable that affects the outcome variable y, but not variable z, then that model also went down. It started with a probability of 0.20 and now has a probability of 0.10. Then model 3, which is variable z only, also went down from 0.20 to 0.16. Now the model that went up, the only model that went up, is model 4, which contains both variables, variable x and variable z. And that model now has a probability of 0.70. So it went up from 0.2 to 0.7. And model 5, which has all the variables and the interaction, went down from 0.2 to 0.02. Now, JASP contains, the output of JASP contains two more columns. One is called BFM. BFM is a comparison of the model against all the other models. And the way this is calculated is as follows. So, first, it calculates the prior odds versus all the other models. So basically, we've got 0.20 for model 1 and 0.80 for all the other models. So if we do 0.20 divided by 0.80, that's 0.25. So it's 1/4. Now, we do the same, but with the probability of the model after observing the data. So that odds is calculated by 0.02 divided by 0.98, and that gives us the posterior odds for that model. So when you do the posterior odds divided by the prior odds, that is the base factor that we obtain here, 0.08. So it's much less likely now than it was before. Well, same for this model 2. Model 2, we first calculate the prior odds of the model 2 versus all the other models. So 0.20 divided by 0.80, which is the probability for combined probability of all the other models. That is 1/4 or 0.25. And then we do the same with the probability, the posterior probability of the model. So we do 0.10 divided by the probabilities of all the other models together, which is 0.9. So 0.1 divided by 0.9. 0.1 divided by 0.9, and that's the posterior odds. Then we do the value that we obtained there, divided by 0.25, the prior odds, and that gives us the BFM, which is 0.44. Went down again. So if the value is 1, it means that the posterior odds are the same as the prior odds. If it is less than 1, it means that the posterior odds are lower than the prior odds. And if it's higher than 1, means that the posterior odds are higher than the prior odds. Okay, so this 0.76 comes from, again, 0.20 divided by 0.80, that's 0.25, and then we do 0.16 divided by the rest, which should be 0.84, and that value is divided by 0.25, and that's 0.76. So again, went down. Then again, we do 0.20 divided by 0.80, which is 0.25, and then we do 0.70 divided by 0.30. So that gives us a value higher than 1, divided by 0.25, that's 9.33. So this is the only model that the posterior odds went up. And this the last model, it started with a prior odds of 0.25, and then it goes much lower because you have to do 0.02 divided by 0.98, and that value divided by 0.25, and that's lower, 0.08. The last column in the JASP output, it has BF10. You can change this to BF01 if you want. We are going to keep it BF10. The other choice you have is whether you have the compare to the null or compare to the best. Okay, so I did both cases, but in the output you only will have one of them. You need to choose which one you want. You can do both, but one after the other. So in BF10, it will calculate the probability of the model, given the data of the model in this line, divided by the probability of the model given the data for the null model. So here in this column we have all comparisons of the model in the row versus the null model. Okay, so BF10 here is 1 because it's the same model. It's model null versus model null. Well, the probabilities are the same, so the ratio is 1. In this case, we've got a base factor of 5 because when you do 0.10 divided by 0.02, when we do model 3 over model 1, is 0.16 divided by 0.02, that's 8 times higher. And when we do 0.70 divided by 0.02 is 35 times higher. And 0.02 divided by 0.02 is the same, is 1. So that is comparing versus the null model. But we have the option to compare to the best model. So you can see that we've got number 1, a base factor of 1, in model 4 because model 4 is the best model. So here we are comparing the best model against the best model. So they have obviously the same probability. Okay, so basically now we've got 0.02 divided by 0.70, and that's 0.029. In line 2, we've got 0.10 divided by 0.70, and that's 0.143. In the third model, we've got 0.16 divided by 0.70, and that's 0.229. And finally, 0.02 divided by 0.70 is 0.029. Now, what is this saying? This output is telling us that the best model, this is a model that is 35 times more likely than the null, is the model that receives more evidence. We can also do base factors of base factors. So if we want to see what's the base factor between 4 and 3, well, remember that the 8 comes from dividing the probability of the model given the data of, in this case, model 3 versus the probability of the model given the data for the null model. Now, 35 comes from probability of the model given the data for the model 4 divided by the probability of the model given the data for the null model. So the denominator in both base factors is the same, so we can cancel that. So basically we can use the base factors to calculate the base factor between these two models. So the base factor between model 4 and model 3 would be 35 divided by 8. The base factor between model 4 and model 2 will be 35 divided by 5. And this will give us an idea of comparing which model is more likely, compare not only against the null, not only against the best, but also against any other model. Here there is evidence that both variable x and variable z are important predictors of the outcome variable y, but the interaction is not. JASP includes another interesting characteristic, which is to calculate base factors over the effects, not models. And it's a clever way of doing it. So what's the effect of variable x? So this is more similar to the traditional ANOVA. So what I explained just now is a model comparison approach. That's not the typical way of doing ANOVA. And the typical way of doing ANOVA is calculating the effects. So this mimics the traditional ANOVA approach. So basically it says, well, what's the effect of variable x? Well, basically what we need to determine is in which models variable x is present. So we've got a variable x in model 2, which is a model that only considers the variable x. We've got it in model 4, in which both variable x and variable z are present. And we've got it in variable 5, which contains variable x, variable z, and the interaction between the variables. So basically we need to add the prior probabilities for all these models. And because the prior probability was 0.20 for each model, and we've got 3 models, now it is 0.60. And JASP calls this the probability of inclusion of that model, and this is the prior probability. For variable z is present in model 3, 4, and 5, so same as the other model, the prior probability of inclusion of variable z is 0.6 before observing the data. The probability for the interaction effect is 0.20 because the interaction appears only in one of the models. The probability of inclusion after observing the data, it does the same as the probability of inclusion before observing the data, but instead of using 0.20 and adding all those 0.20, it will use the probability of the model after observing the data. So for variable x, we've got model 2, 4, and 5. So 0.10 plus 0.7 plus 0.02. That's 0.82, and that's what we noted there. For variable Z, we need the probability for model 3, model 4, and model 5. So that's 0.16 plus 0.70 plus 0.02, and that's 0.88, and that's what is noted here. And the interaction model, it only adds 0.02 because it's the only model in which this variable appears. Okay, and then the Bayes factor for inclusion is calculated with the same way as the BFM. How is it calculated? Well, we've got 0.6 divided by 0.4, which is if variable x is included in model 2, 4, and 5, we need to calculate the odd against models 1 and 3, which they don't include variable x. So that would be 0.6 divided by 0.4, which is 1.5. So we do the same, but the posterior odds is 0.82 minus 0.18, which is the complement of so it's what it needs to get to 1. And that, so this the posterior odds divided by the prior odds is 3.04, and that's the Bayes factor for inclusion. And the Bayes factor for inclusion for variable Z, so we do 0.6 divided by 0.4, that's 1.5, but 0.88 divided by 0.12, and that value is divided by 1.5, and that's 4.89. And with the interaction, we do 0.2 divided by 0.8, and that's 0.25. And then we do 0.02 divided by 0.98, and that value divided by 0.25, and the value we obtain is 0.08 as a Bayes factor. So again, if we are interested in effects and not in the whole model, then we would say that variable Z has a decent evidence in favor of its inclusion. Same variable X, not as strong, but some decent evidence in favor, and the interaction very bad evidence. So the evidence is actually for not including the interaction.